Hey everyone, today we're going to talk about confidence intervals. I'm going to start by giving you an example problem, then we'll talk a little bit about what a confidence interval is, as well as the critical values in two situations. One situation which is uncommon, where we are working with a sample set of data that surrounds a population where we actually know the standard deviation. The other is working in a more common instance where we have sample data, but we don't know the population standard deviation. All we know is the standard deviation of this sample that we've taken. So we're going to take a look at the normal distribution as well as a student's t distribution, which is very, very similar. Both are worked with in a very easy, I think, and straightforward to understand way, so neither of them is more complicated. But let's first of all take a look at this problem. So I've got a manager here that records the repair cost for 17 randomly selected stereos. A sample mean of $82.37 is recorded here. So I've got an X bar of $82.37. That's based on these 17 that he came up with. I don't know what the population mean is. I don't know in all of the stereos that need to be repaired, how much the repair cost is going to be. Because of that, I also don't know what the actual what the actual standard deviation is for the entire population of stereos. So I have a standard deviation for this 17 of $19.66, right? Now, one of the things that we learned about the idea of a sample mean and a population mean is I can guess that the population mean is actually going to be 8237. I can also take a pretty decent stab at a sampling distribution, right? We did some things where you take the standard deviation of a sample and divide it by the square root of the number of things in that sample. And that's going to come up in what we're looking at today. But what he really wants is to determine an 80% confidence interval for the mean repair costs. So let's talk about what that means, because a lot of people think that, we are going to determine that 80% of the repairs are going to be between these two numbers. And that's not really the case. What we're really looking at is a confidence interval where if he were to do these repairs, and this example is if he did samples of 20, if he were to sample 20 of the repairs, right, the lowest and the highest repair costs of that average is kind of shown here. So he did 4, and you'll notice that there was a low and a high on each one of these. Here is the actual population average. You can see it listed right here. Not every single one of these samples actually included the population average. In fact, this one right here did not include that. Out of 20, he's got 19 out of 20, which ends up being, roughly 95%. This looks like a 95% confidence interval that he is kind of constructing, where he can say that 95% of the time when I do this, the average is going to fall between these two numbers, right? That's what we're looking for here. And in order to do this, we have really two options, two formulas that are really pretty similar, and both of them use something called a critical value. One of the formulas is if you know the population standard deviation. If you know that, you are going to use a confidence interval and a critical value that takes the average plus or minus, right? You're going to do an interval. You're going to have above the average and below the average. You're going to have plus or minus, and you're going to use this critical value, a z-score critical value. And we usually see it like this, z alpha over 2, meaning it's a two-tailed z-score. There's going to be some above and below, right? There are times when we're working with testing where we're only interested in one tail, things that go either above or things that go either or below. In a confidence interval, we're looking for both ends, the high end and the low end. So This critical value is where a lot of people, they're like, oh, that looks really complicated. It's just a number. We'd look it up in a table, and we would multiply that by the standard deviation divided by the square root of the number in the sample. Right? This is if you have a known standard deviation. In this problem, we don't. So if you have an unknown standard deviation, we use something that is called a t statistic, right? We're going to use something that's referred to as a student's t distribution, which is just like a normal distribution, except it's a little bit flatter, and it has this idea of degrees of freedom. It kind of gives us a little bit more room for error, if you will. You don't have to necessarily understand all the reasons about it. It functions in much the same way, but we are going to use a t critical value. It looks the same. In this case, we're going to do a two-tailed t-test, and it's got this n-1. This is just telling us with 1 degree of freedom, and we're going to multiply that by the standard deviation of the sample divided by the square root of the number of things in the sample. All right, so this is what we're usually working with quite often. You have to have, when you're working with this, you have to have a probability not a probability distribution, but if you do a probability plot, you would be able to see like, oh, this is going to be a normally distributed, or it's relatively normal. In most of the problems that we're working with at this level, they are going to tell you, assume that this distribution is normal, right? It's not skewed one way or the other. And then they're going to ask you to do something like this. Now, what does this mean? These two values here, this z-score value and this t statistic value, both of them in this case in two-tailed tests, this one with 1 degree of freedom, these things are just found from a chart. All right, there is a chart of z-score values, there's a chart of t-score values. Any statistics chart will show them, and they have them usually broken down by some very common statistics. So I'm gonna show you one. Let me jump over here. Here is a typical confidence interval critical value when you have a z-test. Right? If you're looking for an 80% confidence interval, that number, z alpha over 2, is going to be 1.28. If you're looking for a 90%, it's 1.645, 95% is 1.96, 99% is 2.575. Those would be the actual numbers that you would use for that. And you should recognize them. They come from that idea of a normal distribution and seeing like, well, what values, how many standard deviations to go this far to the right or this far to the left. 2 standard deviations, we always approximate it at 95%, and that's why we're basically saying from the mean, you would go 2 standard deviations to the right, and you would go 2 standard deviations to the left in order to get that confidence interval, right? Now, a t-distribution is a little bit more complicated. I'm going to show a table of a t-distribution that actually comes from the Hawkes Learning site. Whoops. So let's grab that. So in here we've got some tables. You'll see that they have the standard normal table, critical values. It shows a little bit more than the picture I just showed, but it also has a t-table. A t-table in this case in 2 tails. We're looking for, again, a confidence interval, high end, low end. Now this t-table is going to show it a little bit differently. Over here it talks about the value that is in those 2 tails. All right, so if you're looking for an 80%, you'll notice that here they've got alpha of being 2.2, which is 20%. So this would be an 80% confidence interval, a 90% confidence interval, 95, 98, 99% confidence interval. In this case, the question we were looking at says, we need to know the critical value that we're going to use. Since there are 17 stereos, I am going to find a degrees of freedom of 16. and he wants an 80% confidence interval, that's 1.337. That's going to be the value that I would use in this formula. So jumping back over here, I would take my x bar plus or minus 1.337 times the standard deviation divided by the square root of how many samples I have. And again, we had all that information here. The x bar was 8237 plus or minus 1.337 times the standard deviation, if I recall, was 1966. And we had selected 17 stereos. So I'm going to take a moment just to put this together. And remember, there are two problems here. Adding this 1.337 times this quantity and subtracting it. Right? So I'm going to get a high end and low end. But the first problem was actually asking about that critical value. 1.337 was the critical value that we're going to use. All right, assuming that I've done my multiplication correctly, I have 8237 plus or minus 6.3, and I'm just going to round this off to 38. So 8237 plus or minus $6.38, which when I take a look at it, and again, I've done this before, so the rounding might be wrong, I've got $75.99 all the way up to $88.76. And you'll notice my rounding, I rounded it off a little bit different, so 75 instead. But $75.99 to $88.76. That is the confidence interval. That's the 80% confidence interval. What that means is that every time I take samples of 17 like this, I'm 80% confident. 80% of those samples are going to have an average repair cost between those two numbers. Right? If I wanted to narrow that down and say I wanted this to be a 95% or a 99%, the only thing that changes is the value that I would have chosen for that critical value. Going to the chart for the T chart, I would have come up with a different critical value. Maybe it would have been closer to 2 or 2 point something, and I would have used that critical value when I'm calculating this. So when you are working and trying to find a confidence interval like this, you are simply going to need to know whether or not this information tells you the standard deviation of the entire population or just of the sample. Most of the time it's just of the sample. Again, I didn't show one that where we did one where we know the entire population. It's the same process. You just have a different critical value based on the z-score critical values. The t distribution requires you to use the t chart and find the degrees of freedom for that two-tailed test, and that's where I got the 1.337. So hopefully that will help you do a confidence interval 80%, 95%, 99% using a student t distribution.